Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Let's start problem 4.3. The statement of problem is given that using an allowable stress of 155 megapascal determine the largest bending moment that can be applied to wide flange beam shown, neglect the effect of fillets. So this is a wide flange, the cross section of wide flange is given and the moment is also shown. You have to determine the value of largest moment that can be applied. Clear? So given data is that in given data you have been given the allowable stress. So sigma allowable is equal to 155 megapascal, which is equal to 155 into 10 raised to power 6 Pascal, and you have to find the largest moment, bending moment. You have to find this moment M to this flange. So as you can see that this is the wide flange having the width of flange is 200 millimeter, the height of this beam is 220 millimeter, the thickness of this flange is 12 mm while the thickness of web is 8 mm. So let's start with its solution. So as you know that this bending stress is equal to My or MC divided by I, where M is the bending moment, C is the distance from this neutral axis to the topmost. You have this is 1C and this is also C, but it is downward, so we will take this distance as negative and this distance as positive. So from this we have to calculate M. So M will be equal to sigma into I divided by C. So basically this is the formula from which we can get the moment. So this stress is given, which is allowable, sigma allowable. We do not know I, and C will be calculated from this figure. So let's start first calculating the value of I. Now I is equal to, basically you have to find the value of I for this beam. So again we will divide this beam into 3 portions. So let me draw this. This is the top flange, this is the web, and this is again the bottom flange. Clear? As total height is 220, so its centroid will pass through half of 220. So this is actually your C. So this is your C, and that is equal to 110 millimeter. Because C is the distance from, this is neutral axis or centroidal axis, and distance from neutral axis to the topmost is the value of C. Now we will divide this wide flange beam into 3 portions. The first one is this, the second one is this, the third one is this. So basically the I formula for this rectangular will be 1 over 12 BH cube plus AD square. Now you will confuse about what is AD square. So if you go back to the previous problem, just like in this problem in which you have calculated the value of I, which was just 1 over 12 BH cube in I outer and in inner, there is no A plus D square. Why? Because this centroidal axis is actually passing through the center of both the rectangles. Similarly, in this problem you can see that this is the neutral axis and it is passing through this triangle rectangle which we discussed, this rectangle, the part 2, and this third one. So if your centroidal axis or neutral axis passing through centroid, so D will become 0. So you can see, let's start with the first one. So I1 will be equal to, what is the value of B? This is B, 200 millimeter. So that is 1 over 12 into 200 into height is the thickness of this, which is 12. There, 12 power 3 plus area. Now this is the area of this is thickness into its width. So which is equal to again 200 into 12. Now what is D? D is actually the center distance of this rectangular section, because now you can see its center is not passing through centroidal. So this distance is actually D. And this D is how much? This D is the distance from this axis to the center. And this center is, this distance is 6, and this distance is, you will calculate it. It's a little tricky, but you will calculate. If you subtract 220 minus 24. Why 24? Because 12 is this and 12 is this. So it will give you 196. So 196 is the distance between this point and this point. This is 196. So again, if you divide 196 by 2, that will give you the distance between this point. So let me calculate the distance. 196 divided by 2 will give you 98. So basically distance from this point to this point is 98. No, sorry, distance from this point to this point is not, this distance from this point to this point is 98. So if you add 98 with 6, so it will give you 104. So this distance is actually 6. So now from this point to this axis, this is the D. This is D, and this D is equal to 104. So AD square, so that will be 104 whole square. So I1 will be equal to, if you calculate, this will be equal to 25.98 into 10 raised to power 6 mm4. So this is the moment of inertia of this, the first portion. Clear? And as you know that this I1, the moment of inertia of I1 and I3 will be same. So it will also equal to I3. So now you have find I1 and I3. Now we will move toward I2. So I2 will be equal to, now what is I2? I2 is actually the moment of inertia of this. Let me show it with another color. So this body is actually body number 2. So moment of inertia of this body will be, if I write the same formula, 1 over 12 BH cube plus AD square. Now you can see that 1 over 12, what is the breadth of this, which is given above, that is 8 mm. You can see this, the width is 8 mm. So that will be equal to, B is 8 and height is actually this height is, we calculated earlier, is 196. So height will be 196 cube. Now what is its area? So 8 into 196. Now you can see that this centroidal axis here, or neutral axis, is passing through its centroid. So definitely the value of D is equal to 0. So this whole term will be equal to 0. That's why we do not include A into D square with any moment of inertia of body which passing through its centroid. So I think this concept is clear to you now. So I2 will just simply 1 over 12 BH cube are equal to 1 over 12 into 8 into 196 power 3. So when you calculate I2, so I2 will become equal to 5.01 into 10 raised to power 6 mm4. So now total overall inertia, let me choose another color. Overall inertia I will be equal to I1 plus I2 plus I3. So you have I1 and I3 as well. They are same, and I2 is given over here. So put the value. So I will just write simply I1 and I3 are same. So I will write 2 into 25.98 into 10 raised to power 6 plus the value of I2, which is 5.01 into 10 raised to power 6. So the final value or the moment of inertia for whole wide flange beams come out to be 56.94 into 10 raised to power minus 6 meter 4. Clear? So we have find I value. Now we will move toward this upper formula, which we wrote that this M will be equal to sigma into I divided by C. So sigma allowable is given, that was 155 into 10 raised to power 6. I is also given 56.94 into 10 raised to power minus 6 divided by, now C is the distance from neutral axis to the topmost, which is 110. So millimeter. So we will convert into meter, which will be equal to 0.110. So again, if you calculate this, the moment, the value of moment comes out to be 80.2 into 10 raised to power 3 Newton into meter. Or simply you can say that the value of moment is 80.2 into 80.2 kilonewton into meter. So this is the value of bending moment that can be applied, maximum bending moment that can be applied on this beam. So this is the beam. This is the beam, and the axes were shown like this is the center, this is the x-axis, and this is y-axis. So moment of the moment can be applied. This means you can apply the moment M or 80.2 kilonewton to this beam. So this was the solution of problem 4.3. Thank you for watching the video. If you have any question, you can ask.